Rosie Newhan, and this is the one about compound interest. Okay, let's first remind ourselves how we increase a number by a percentage. Here's a number we need to increase, 180. So, two methods really. One is this sort of obvious way in which we would find 20% of that number and add it. But that's got two steps, so we don't want to do that. And also, it doesn't help us sort of understand the compound interest formula. So let's look at the better second method. So just to say, yeah, here we found 20%. Remember, we can easily find 20% by multiplying by 0.20. I just want to remind you that those first two digits after the point in a decimal number represent the number of percentages. So much easier to work with that than fractions. But if you need to think of 20% as 20 over 100, that's fine, but decimals are much easier. So that means 20%. So we can find 20% by 180 is 36 and add it to the original number, and we have got 180 increased by 20%. But let's look at the second method. Now, adding 20% to the original number is exactly the same as finding 120% of that original number. Yeah, the 100% of 180 is 180, plus we're adding 20%. So we're adding that 20% all in one transaction. So what does that look like? Well, we can multiply the 180 by 1.2 and we get the same value. And the 1.2 is sort of an interesting number because look, multiplying by the 1 bit keeps the original number the same, and the 0.2 adds 20%, which is pretty clever. Some more examples. I just want to get the hang of this because it's quite important. So increase £50 by 60%. Well, what we're going to do is we're going to say it's equal to 50 times 1.6. So the 1 will keep the 50 the same, the 0.6 will add 60%. I've got the answer there, so I don't have to do it in my head. This will be equal to 86 times 1.175. Now the first two digits after the decimal place are how many whole percent, and then if there's any decimal places, then they just come after that. So when we see that, we can see that as 117.5%. So important that we can recognize that. Just on the side, so 0.2563 as a percentage is 25.63. What would 0.025 be, written as a percent? It would be 2.5. So the first two digits after the decimal place give you how many whole percent? So there's only 2 whole percent there. So we need that sort of 0 there as a space holder. Anyway, that was an aside. So 24 by 3 by 35% would be like multiplying it by 1.35, and this would be 300 times, oh, here we are, we have that exact same situation, 0.25, that's 2.5%. All right, so you'll see that idea coming up in just a moment. What about we have to decrease a number? Well, we can do the same thing. We've got the same old boring old method 1. We can find 30% of it and subtract it and get 105. That's okay. But it doesn't help us when we're getting more algorithmic later. So let's look at method 2. Now it turns out that subtracting 30% is the same thing as finding 70% of the original. You're like saying, there's 30% I'm not interested in, so I'll just find the 70%, and it will already have had that 30% eliminated from it. So this is the same thing as finding 70%, and here it is. So 150 times 0.7 gives us 105. It's leaving behind the 30% that we don't want. Some more examples. So how do we decrease 65 by 20%? Well, it's going to be 65 times. So we want to leave behind our 20%. So all we want is 80%. So if we multiply it by 0.8, we'll get 52. Here we're going to say that's equal to 20 by, Oh, I've got to do some maths here. That means that I've got to, let me think, it's going to be multiplied by 9. Oh, goodness gracious me, I can't do that in my head. What is that going to be? 96, 5 possibly. If I add 35 to that, then that would, yes, so that will be right. Okay, you can see what I'm doing is taking 100% and subtracting 20. So, all right, this one's going to be 56 times 0.66. Hopefully 66 adds up to 34. Adds with 34 to make 100. All right, so finding 66 will leave 34% behind because we don't want it anymore. This will be 100 times 0.05. Because we're saying we want to get rid of almost all of this, 95% of it. So all we're interested in is really 5% of it. So there we go. Let's get rid of these. I hope I got that numerically correct. All right, so first of all, simple interest. What's simple interest? Well, simple interest is, by its name, very simple. If we have a simple interest of 5%, all that means is that this investment in our bank or whatever, they'll calculate 5% of it, and then every year they'll add that same amount. So the amount of interest added stays the same. So let's see what that looks like. So we need to find 5% of 1,000. So multiply it by 0.05 will give us 50. And then how much we will have at the end will be the original 100 and 10 lots of 50. So every year we got £50 interest. And so the amount of interest never goes up, it stays the same. All right? But now we have compound interest. Okay, famously quoted by Einstein as being the 8th wonder of the world. I rather suspect that by the end of his life, he had quite a bit of money accumulated and was quite fixated on this. Compound interest is a sort of good thing if you own assets, of course. He's saying that, yeah, he who understands it earns it, who doesn't pays it, because you don't want to pay compound interest, you want to gain compound interest, and this is why you want to earn it if you can. So the pink bars are simple interest, so going up by a fixed amount every year, like we saw with that example. But compound interest gets exponentially bigger. The greater the number of years, the bigger the difference between them. Because what we're doing is earning money on the interest that we've earned so far. So let's have a look at that. So Aisha has £500. She invests for 4 years, earning £5 compound, 5% compound interest. All right, so we've already seen how to add 5%, haven't we? So after year 1, she will have her 500 times 1.05. So that's how we add 5%. Great. At the moment, it looks like simple interest. But now, it doesn't look like simple interest, because at the end of the second year, we take the amount she had in the previous year and find 5% of it. So now she's earning interest not just on the 500, but also on the interest she earned the year before. And this continues for 4 years until she's got that amount. But we could say, we could write it like this, couldn't we? 500 times 1.05, and then we could use brackets or not, it doesn't matter. And then for the second year, we have to multiply that whole thing by 105, and then the whole thing by 105 again, until we get that amount. Now, those of you who know powers, which I hope is all of you now, we can shortcut that because we know that that's 1.05 raised to the power of 4. And we get the same amount. So now we're ready for the big formula, and here it is. Compound interest. You learned this at school. Let's just remind ourselves. The amount at any point will be the original amount, the principal amount, times 1 plus r, where r represents the interest rate, all raised to the power of n, which is the number of years or the number of periods. All right, and we were just looking at an example of Aisha's investment, and we found that it was 500 times 105.4. So hopefully you can see that if we're looking at 5% interest rate, then r is 0.5 0.05, and it always gets added to that 1. Remember, the 1 keeps the original amount, and then R adds your additional percentage. Okay, so if we're looking at 3.5%, then R will be 0.035, and so on and so forth. So the big equation, or the big formula. But economists tend to write it just a little differently, just subtly differently, because they can't take anything as other people have them, obviously. And here we are, the economist view. So they're going to be talking about the future value of something is equal to the present value, because the economists have to worry about time, as do bankers and accountants. We have to worry about the time zone we're in at the moment. So future value is a function of present value times 1 plus r raised to the t. We tend to use t because we're looking at time, because we graph this a lot. So t will be along the horizontal axis. So there it is. That's the big formula. We're going to use this a lot, and we're certainly going to use this a lot in later videos when we're talking about present value analysis and net present value analysis. Okay, let's just sort of see how it works. Let's get rid of this. So your house appreciates by 3.5% each year. It's valued at 120,000 now. What will be worth in 8 years' time? Okay, I don't really need a pen for this. Okay, so here's a reminder of our equation. So the present value is 120. Yeah, it's now present value, and we're going to multiply it by 1 plus r raised to the power of 8, and there we have it. So that's how much it's going to be worth in 8 years' time. So it's nice and easy. How about another one? Aisha invests 500 for 4 years, compounding at 5%. So how long will she have after 10 years? Well, she's going to have 500, original amount, times 105, raised to the power of 10, and that's how much the investment will grow to. So just out of interest, how long would it take for her money to double? Well, it obviously hasn't doubled in 10 years, so it's going to be a bit more than that, isn't it? At the moment, we can only do trial and error. Let's do that. We can see that we can try 14. Oh, and that gets us pretty close. If we get 15, we get over. So we can look at this and we can say, oh, right, so it's in about 14 years, the amount will double. But we don't really like trial and error. So later, we're going to use logarithms to be able to answer that question exactly. So more on that later. I'd like to leave you something to look forward to. Logarithms, big topic. We'll have videos on that. All right, so now we've only been talking about increases. Let's think about depreciation, because unfortunately not all your assets appreciate, they depreciate. Cars, famously so. So cars worth 24,000 in 2014. Oh, I've used this before, I've never noticed that before. Too many zeros in there. 2014. How much will it be worth in 2018? So we looked at this before, didn't we? Each year we need to depreciate by 15%. So that means that we can find 85% each year, because we're only interested in 85% because the 15% unfortunately is lost to us. So after 4 years, the value of the car will be, so 24,000, and then 4 times, because 4 years here, 4 times we're going to multiply by 0.85, the sort of discount factor, and which is the same as this. So we've used our compounding formula again, and we found the answer. So what does this tell us? This tells us in this depreciation situation that R is actually a negative number. So it's minus 0.15, which means that when we find 1 plus R, because that's what our formula asks for, it becomes 1 minus 0.15 equals 0.85. So that's our compounding amount. All right, so just like we decreased by a percentage before, we can do it inside the compounding formula. So it works in the same way. So every year it's decreasing by 15%. So just to say, compound interest is a function, and it's a function economists use a lot. It's often referred to as the wealth function. So W for wealth, and it's sort of, this is always sort of known as the growth function. You'll see a lot of this for those of you who study more and more economics. So wealth equals the principal 1 plus R times T, which hopefully is beginning to look familiar to you now. So here's a spreadsheet that's sort of calculating this, which that's nice and easy. All right, so for instance, this is a spreadsheet I put together, and in that column, in that cell there, so here's the formula I used. So it's 1,000 because that's our principal amount. Here's my 1 plus R plus R, and the rate my spreadsheet is picking up from cell B2. B2. So these column headings are actually being used in the calculation. So that's a 1%. And I'm raising to the power of a 4, so I'm raising it to the power of that number. So all these numbers are derived in the same way. So this is what we raise to the power of, these are what we use as rate, and we can plot it, good old Excel. And what do we notice? Well, we notice something very obvious, actually, that the bigger the interest rate, the quicker your wealth is accumulating. It's no surprising that Einstein was so keen on it, isn't it? Okay, so we can start actually making direct comparisons of what happens with different interest rate scenarios. Right, and because the increase is constant, if we find the log graph of it, and more on this when we study logs, we get straight lines. That's because the growth rate is constant for each of those. You see, it's going up in ratios of 2, so that's a log scale chart. That's it for this video. I'm just going to put some practice questions up, as I always do. And so freeze frame and have a go at yourself, and then I'll put solutions up. And then I've actually got 2 pages of questions, so there'll be question solutions. Anyway, good luck with them.